So we're talking a little bit about some of the context of these ideas of reduction potentials and cell potentials beyond just making cells to kind of some other broader chemistry. So we know that this cell potential describes spontaneity, right? Does this process happen? And normally, we just kind of plug in our cells and we see, do electrons flow? What direction are they going to flow? But we can also understand when we we mix reactants together and force the reaction, or try to have reactions go in, say, something like these single beaker reactions, where you just put a metal into a solution containing cations of a different metal. So if you mix, say, copper 2+ and zinc, you would be doing the same redox chemistry of having copper be your reducing and having zinc be the oxidation, right? Because you've put these reactants in together. You haven't separated them by a wire. So you've set what is going to reduce, what's going to oxidize. You can figure out the cell potential. And that cell potential is greater than 0 volts, meaning it's a spontaneous process. If instead you mix, say, copper solid and zinc 2+ cations, right, now you're determining this is what the reaction has to be, right? This is what the reaction has to be. And then you're saying, what is going to be the reducing, what's going to be oxidizing. And then the cell potential is going to be negative, which makes it not spontaneous. That's why this beaker just looks like a piece of copper reactant in a solution of zinc cations, which are the colorless solution. So it's not spontaneous because the cell doesn't flow in that direction. You haven't put any, say, zinc solid in there. You haven't put any copper in there that could react in this other direction. So if along the same lines, these potentials really point to what the tendency for these reactants is. And kind of the extremes of the table are only going to go one direction. So for example, these things over here, things like fluorine, hydrogen peroxide, chlorine, oxygen, these are really good oxidizing agents because they have these crazy high reduction potentials. They are almost always going to win when you ask the question of which one has a higher reduction potential. So they're going to be really, really good. And that's why we can understand why fluorine is such an aggressive reactant, because it really, really wants to gain electrons and become fluoride. Oxygen wants to become, it wants to react and produce water or produce hydroxide, whatever you're looking at. But these things, chlorine, these things want to react. So these are all of these kind of things that are reactants, and these high potential reduction half reactions are very strong oxidizing agents. At the same time, these, products over here on the very low negative or the very low potential reduction reactions, that very low potential that we see over here implies that the opposite direction tends to happen. These half reactions down here almost always lose the battle of why don't we swap it the other way, right? Which one has the higher potential? So these always get swapped. Those products in here, things like hydrogen, aluminum, magnesium, sodium, lithium, are all going to be very, very good reducing agents. They really want to oxidize because the opposite direction, the direction of the reduction, is pretty weak, right? Those are pretty negative. So one of the applications of this is looking at the reactivity of metals. So pure metals, they only form cations, and so they tend to only react via oxidation, loss of electrons to create those cations. So this is reverse reactions of what we looked at before. So lithium, we're normally looking at reduction. Lithium is up at the top here. It's at the bottom of our reduction table. So it is really good at oxidizing, being oxidized, right? It wants to undergo oxidation, which means it's a good reducing agent. It makes the other thing reduce, right? Kind of got those swaps. So these metals up here react with water. They are so reactive. We call this an activity series. These are the highest activity, which just means how many chemical reactions. These are kind of binned by reacting with water, reacting with H+, reacting, or steam, reacting with H+, or not even reacting with H+. And so things down here, we can see copper, silver, platinum, gold. They're very unreactive metals because really the main type of metal reaction is oxidation, and they're bad. They don't really want to do that. And so we can understand these things. Now, at the same time, the cations that are created by it would again be very reactive because the metal, without having lost any electrons, is really stable. So these copper 2 plus, silver plus, gold 3 plus is extremely reactive, because gold element is very unreactive, right? This side is very unreactive, which means this side is extremely reactive. It really wants to take electrons from other things. It's a very good oxidizing agent. And so, we can understand this activity series. Sodium is near the top. The oxidation potential, so the negative of its reduction potential, is positive 271. It just burns in water, or it oxidizes in water. It is so exothermic that it makes hydrogen gas in the redox reaction, and it's so exothermic that the hydrogen gas just spontaneously ignites with oxygen in the air. It's just so hot that you make hydrogen and immediately burn it in the air. Gold, on the other hand, has a really negative oxidation potential. These gold really doesn't want to lose electrons. So that's why we use it for things like coins. You wouldn't want to use sodium, because if you made a coin out of sodium, it would burn in the rain, right? Or decompose in the rain. That's not good. So the copper and nickel families on the periodic table are called the coinage metals. They tend to have really negative oxidation potentials. So as a result, they don't react with water, air, acid, or anything like that. They have a really high resistance and high longevity. They're going to exist for a long time. They don't degrade. And that's why we use them for coins, because you don't want your money to die. Right? If the coin literally dissolves, that's going to be a problem. So one thing we want to return to is, if we look back at this activity series, aluminum is real high up. In much the same way that we don't want our coins to react with water, we also don't want our building materials. So aluminum is really reactive, but we use it in buildings all the time. This is a picture of an aluminum roof. Aluminum cans have a really long shelf life, all this kind of stuff. So what's going on? How can this happen? Why do we use aluminum even though it's really reactive? Because magnesium right here, you would never use as a building material. It's a similar reactivity, but you can't use it as a building material because it corrodes, it dies really easily. So what's the difference? And the important thing is that aluminum is so reactive, it actually reacts with the air. But the important thing is that when it reacts with the air, it makes this oxide layer that functions like a cover, so similar to paint. And what happens is it makes just a cover that basically protects all the metal down here. So yes, this aluminum is super reactive. It would gladly react with this oxygen, but when the oxygen molecules come down and touch, say, the aluminum surface, they're not colliding with fresh aluminum metal, that is your reactant here. Instead, they're colliding with already reacted aluminum metal. So it's really a kinetics issue. The thermodynamics, the aluminum atoms, happy to lose electrons, but they basically just can't collide with those oxygen atoms. You also note things like iron is relatively reactive. Chromium, again, that's why we paint things, to prevent that cover. That's a kinetic protection. And aluminum just naturally does it. These other things don't naturally do it. Aluminum naturally protects itself by the formation of basically already reacted aluminum that just covers the surface. All right, leaving metals for a little bit, we're going to talk about bleach. The bleach is NaClO, that's sodium hypochlorite. So if you dissolve that in solution, it's an ionic compound, so you have the sodium and the hypochlorite ion. The sodium isn't doing much, but the hypochlorite can do redox chemistry. And its reduction potential ain't bad, 0.89 volts. That's relatively high, that's pretty high. And so it's a pretty good oxidizing agent because it has a relatively high reduction potential. It wants to gain electrons and it'll take them from other things. And so, it wants to gain electrons. Any molecule that is easy to take electrons from, bleach will react with. So dye molecules, things that we use to color things, tend to have a lot of double bonds. So for example, this is indigo blue. So we've got this kind of modified Lewis structure. Everywhere that the lines connect is a carbon. So there's lots of carbon here. It's one of those organic molecules. And you'll note there's this double bond in the middle. And the ClO- wants to take electrons from anywhere it can. And the electrons in this double bond are relatively easy to take. So what happens is the hypochlorite reacts with those two electrons, takes them away, the molecule falls apart. Instead of being blue, it's now colorless. So this is how bleach works to, quote, bleach things. bleach takes electrons. A lot of colored molecules have a lot of double bonds, a lot of kind of extra electrons, very high electron density. So it's relatively easy to take those out of the molecule and lead to a colorless molecule that no longer has those kind of double bonds or things like that. So bleach is, and you'll note one of the reasons why we use bleach as opposed to, you wouldn't, other super, this is like pretty positive, but not crazy high. That's why we can use bleach. It'll affect, say, the colored molecules, but it won't degrade like the actual fabric. If you used something like, say, fluorine, really, really, really high reduction potential, it wouldn't just destroy the dye molecules, it would destroy everything. So bleach is just, it has a pretty high potential, it's 0.89, non-trivial, but it's not crazy high that is like dangerous. You can use it in your house. It's going to focus on taking basically the easiest molecules to take electrons out of. It does the same thing when you use it to kill living things. Most living things, most of their molecules want electrons. And so bleach will just kind of take the lowest, easiest common denominator, whatever the easiest molecules to oxidize are, and kill them, and then usually the bacteria die. Oh, and you can also bleach using other things like hydrogen peroxide. Hydrogen peroxide also has a decently high reduction potential. So again, and it's a little more gnarly than bleach is, so we tend to not use it, but you can, you're using it at really low concentrations if you buy it at the store. So if you put it in your hair, it'll bleach your hair, it'll kill the dye, it'll kill the colored molecules. Okay, kind of cool little applications. No participation questions in this video. 4.7 is what we're looking for. Got a couple more videos left, one kind of last topic in this set of videos, Nernst equation. I'll see you there.